Okay.
Okay, so, you know, the other function z equals f of x, y, here it is. We're going to confine this to the plane y equals 3, giving you a function of one variable. We want to find the derivative at x equals 1, derivative of this function. We want to graph the function and show the meaning of the derivative. Now, everything up to here is pretty straightforward. We'll do that in a bit, but people are having trouble doing this graph, and it's a simple parabola. So you really need to understand how to graph these things from pre-calculus. Now, what you should do in pre-calculus, the way it should be taught, is, okay, you've got to get this function z equals 9 minus 2x squared. That's going to be a function of one variable. We'll go through the details of that rather quickly, because I think everybody pretty much gets that. But there it is. How do we get this graph? We start with the graph of y equals x squared. And we know that to be a parabola with a vertex at the origin. And we should know, you know, what some basic points are, because you have these toolkit functions and basic functions in pre-calculus. Almost everybody does pre-calculus in terms of those functions. Whether you did in your course or not, I don't know. So we start with the y equals x squared function. Now, if you double x squared, well, okay, start with this function. We multiply x squared by negative 2. What's that do to the graph? Well, x squared is this distance. You know, to this point, for this value of x, there's x squared. Okay, if we double it, then it gets twice as big. The value of x squared gets twice as big. The point would be up here. But of course, it's negative 2, so it's down here. So this distance down and down again gives you the point on this graph. And if you do that for a bunch of points, you'll see clearly that the graph goes like this, but it gets a little skinnier. Okay? Every point gets steeper. Every slope gets doubled. It goes negative, because all the rises, and for any given run, the rise of this thing will have twice the magnitude as it does here, for reasons that you should think through and should be pretty obvious, but maybe require a little thinking. And they'll be negative. And that's the constant rule, basically. Well, you do this, then you add 9, and you've got this function. So you just take all the points in this graph, raise them up 9 units, and there you've got an upside-down parabola. Now, to locate it, it's obvious that this point, which transforms the origin, has to be 0, 9. But we can confirm that, okay? When you graph a function, you always want to look at where the intercepts are. You also want to look at where it's rising, where it's falling, where it's concave up, where it's concave down, just using your derivative test. But at the pre-calculus level, which is all you really need to get this, you look at the intercepts. And then you're going to have a good picture of the function. You know it's a parabola. You know it goes through 0, 9. You know that even if you hadn't done the transformations, but you really need to graph the transformations. And then the zeros happen when z is 0. Well, z is this, so when z is 0, this is 0. There it is. Simple equation. X is plus or minus 3. Excuse me. So we got the point. Negative 3, 0. And 3, 0. Those are the x-intercepts. Gives you a pretty good picture of the function. So now you're asked for the derivative at x equals 1. How do you interpret that in terms of the graph? Once you have the graph, what's a picture that shows the derivative geometrically?